Thanks for coming to the talk. Thanks for inviting me, Stephanie, and it was a great dinner last night. Bill and Dick, Stephanie, it was great. And before I forget for anyone, so I'm at Ohio State and I'm like best friends with Jean Lafon. That's who I work with. None of this is with him, but he says hi to everyone who knows him. He wanted me to, I'll forget if I don't say that now. So, all right, so yeah, the isometric embedding problem for length metric spaces. Let's first quickly discuss what I mean about isometric embedding, because this gets a little confusing. So maybe part one of the talk is about path isometries. And now this will look bad, but if I write lower here, no one will see it, so let's go up here. So kind of definition-ish, we put quotes. This is a terrible definition. In this talk, for this talk, it's a local definition. For this talk, isometry is going to mean path isometry. And again, after the talk, you can go back to put a not equal there. It's a local definition. But what's there, i.e., because I'll keep forgetting to say the word path. That's why I want to stress this at first. i.e., anisometry for this talk, now I'll explain the difference here in a second, is a map, is a continuous map which preserves the lengths of paths, which, always continuous, which preserves the lengths of paths. All right, real stupid example to get the point across, right? So let's take, again, easy example. Let's take S1, right, unit circle, and let's embed that into R2, right? That's one thing. It's good. Let's call this point, out of lack of creativity, N. Let's call this one S, right? And it's abuse notation and still call that N an S, even though let's give us some name, inclusion, iota, right? If you look at the distance in S1 from N to S, right? Distance over here, right? Quickest way you can get on the circle is going to be like pi. Pi r, we have pi, right? Looks bad if I mess that up. But of course, if you look over here, distance in the plane, right? Between iota of N, iota of S, I'm cheating, right? Shortest distance over here is 2. And rumor has it, those aren't the same, right? Those aren't the same. But this is not a metric isometry, but it is a path isometry. Preserves, by definition, preserves the length of every path, right? And so this is an isometry in this talk. This is what we want. This is exactly isometric embedding, whereas not. So this is iota is not a metric isometry you pull out, baby Rudin or Mungries or something, right? It's not a metric isometry, but is a path isometry. So this is what we're going to be talking about. So this is an isometry in this talk, path isometry, preserves the lengths of all paths. Okay, let's get that out of the way. Real quick remark. Some goofy about path isometries is they don't have to be injective, right? Path isometries need not be injective. All right, stupid example. I'm going to call the function this, which goes from R to R, greater than or equal to 0, right? Absolute value, take any number that's absolute value. That preserves the lengths of paths, right? You just take half bend on the top, right? Any path, right, that went into the negatives, right? It still has the same length, right? You just mapped it over. Does that make sense? In general, any reflection through a hyperplane, right, in Rn, right, it'd be a path isometry, not injective, or any composition of those. Is that all right? You want to see? All right. All right, so it's part one. Part two, maybe the major part of the talk, or at least the famous part. Known results for manifolds. So several different results I'm going to list throughout this talk. These aren't going to be the most formal statements. I'm not going to write theorem and all the stuff. It's just going to be more schematic, but I'll try to say all this stuff. So the first major result, the famous result, is solved due to Nash. Right? It's the famous Nash isometric embedding. Yeah. There you go. And so the idea, you look at the collection of n-dimensional Riemannian manifolds. And Nash proved two results, two different papers. The first is that these always admit C1 isometric embeddings into Euclidean. I always put the E to stress the dot product, Euclidean dot product, specifically into E 2n plus 1. You can actually say something a little stronger than that, and I'll mention that later. But that's terrific. That's about as low as a dimension as you could hope for. But of course, C1, right? Then a couple years later, Nash proves that you get smooth isometric embeddings into E, some giant bigger dimensional space. I'll write down the known n here in a second, right? So when Nash proves this, I think the paper's from '56. If you look at Nash's paper, you'll see big n's on the order of n cubed, little n cubed, but then it's been reduced, right? So the first you see these results was the first thing you could try to do, lower that dimension, right? It's the first people worked on. And so the state of the art, I guess state of the art, the best known capital N, I'm going to forget this, so let me look here. It's the maximum of S sub n plus 2n, S sub n plus n plus 5. What is S sub n? S sub n is the number of independent entries in an n by n symmetric matrix. N times n plus 1 over 2. Right. I'll explain that further, but let me put some names to this. The first person, of course, was Nash, who got capital N. It was then reduced by Bob Green around 1970, and then at the exact same time by Gromov, right, independently right around 1970. I don't know whose was lower. I think Gromov's, but it was close. But then it was Gunther who got this bound, late 80s. I think it's the best anyone's gotten since then. These I've all read, real geometric. It's PDE paper. Not an expert there. All right, so yeah, where does this S sub n come from? Real fast. If you fix if you have a point on your manifold, you fix a local frame, right, x1 to xn, and then look at the Riemannian metric. You've got your right. Once you fix a frame, you can code it as an n by n symmetric matrix, and this is just 1 plus 2 plus. It's just the number of independent entries in a symmetric matrix, right? Stop. Going all right? This makes sense. All right, it's the number of components of the metric tensor. Maybe it's worth.
So I take it in all these results by symmetric embedding, we mean what you just.
Path isometry, yeah, and actually that's the next remark, right? So in Riemannian geometry, right, when you say isometric embedding, you mean a map where the pullback metric coincides with the intrinsic Riemannian metric. You mean a map like this, where if you pull back the dot product, it's the same as your intrinsic Riemannian metric you start with. So now's the time for the remark. I won't use this board again. Sorry, people over here. I'll read this out real quick. If you have a Riemannian manifold and a smooth path in M, then you can define the length to be just integrate just your normal dot product square root, right? Everyone seen this. And then the energy, just erase the square root, right? Energy. And you can prove it's not hard. That a path preserves the length, a map preserves the length of all paths, if and only if it preserves the energy of all paths. The quantifier is important, of all paths, if and only if the pullback metric coincides with the intrinsic Riemannian metric. So of course, when Nash proves this, he uses this because you're at least C1, so you have at least one derivative, so you can pull back the dot product, right? But if you want to try to extract this to general length metric spaces that aren't manifolds, you don't have calculus, but this is the equivalent notion, right? In Riemannian geometry, you'd want to use this one here, right? Or one of the one of the two. Is that, everyone see that? This is the point of, all right. Good. All right.
Well, there's a question that led from this, right? Because these path isometries don't have to be injective. So you could imagine just taking like a sphere made of gold and mashing it with a hammer into a plane and then mashing it with a hammer into a line and into a, and that would be a path isometry.
Mm-hmm.
And then you could stick that anywhere.
So the next known results, that's good. I'm going to talk about that right now, is due to Gromov. And so the smashing into a line is tougher because from dimensional purposes, but you could smash to the same dimension. That's the Gromov stuff. Real quick, all right, so if you're going to look at these Nash results and you want to try to do something tangent or generalize these, what would you try to do? First is lower that dimension, but you'd work on that. So what else could you do? You could try to look at something C0, right? But C0, you don't have pullback metrics, but you do the path isometry, right? Or you could try to look at different types of metrics, different types of structure here, manifolds with some other type of structure. Of course, if you do that, you're going to have to change what spaces you're mapping into, right? And so the next results are just those types of statements. And the first one, which I 2, that was 1, right? This is due to Gromov. And it's that if you look at the collection of n-dimensional Riemannian manifolds, these admit, this way, C0 path isometries into n-dimensional Euclidean space, the same n, not an embedding. Right? In general, this has absolutely no shot to be an embedding due to dimension reasons, but it just path isometries into the same dimension. And ruined my punchline, but that's okay. I don't know if it was Gromov, maybe it was Dima Barago, I don't know who came up with this. Someone calls this now the elephant map. At least I know it's definitely written as the elephant map in a course in metric geometry, the Barago-Ivanov book. So it definitely, someone in that book. Huh? It's not an embedding. Not, oh, you got to stress it. Not an embedding. In general, right? And you see, why do they call it the elephant map? Is take S2, right? This is the description. Take S2, set it on the floor, and have an elephant step on it. That's a path isometry into R2, right? And so that's the, right? It's not an embedding, right? But matter of fact, it's not differentiable on at least a dense set, right? For sure, because of curvature reasons.
It's not a local isometry, but no local embedding either.
No, not at all. Correct. Not a local embedding. Yeah, and again, it's C0 right over here. And it's not, the points where it's not differentiable have to be dense, right? So yeah, correct, right? Kind of a goofy pathological map. I think the proof of this is H principle. I think he's pretty deep, right? I think he cooked this. I think it's his big PDR book. But so, all right, so it's 2, it's 3. Third one here is now we're going to change the type of forms you have on your manifold, right? So this is independent by Bob Green. And then the other paper I've seen, it's a joint paper. It's Gromov and Rockland. I just learned recently was Gromov's advisor. Anyway, Gromov and Rockland, they look at the collection of n-dimensional manifolds with indefinite metric tensors. Or people want semi-Riemannian, indefinite metric. I'll keep it like that because maybe I didn't word this correctly at dinner last night. You have your manifold. What do I mean here? You have your manifold. You've got a symmetric bilinear form, smoothly associated to every point. But the eigenvalues don't have to be positive. They can be negative. They can be 0, right? This can be degenerate, right? It doesn't, right? And they prove that these things admit smooth isometric embeddings into what do we got? R, Q, comma Q. And what is Q here? Q is n over 2 times n plus 5. And at least this is the Q you get when M is compact. I didn't write it. I think I wrote down the compact case. I found that pretty quick, right? So in the order of n squared for each one of these, and it's nice, but of course, right, there's a lot more freedom going on there. Who's that? Good. Oh yeah, so it's worth pointing out before I go to the next one. Most of this talk is statement of results. I'll sketch a few proofs later. I'll at least draw a picture in a couple minutes for this one here, the C1. Talk about that in a second. So not lots of proofs, but if you guys have questions, there's a lot of inverse function theorem. The proof of this is very similar, but simpler to the proof here, the smooth isometric embedding using the inverse, Nash's inverse function theorem. So, all right. So third, last one of these results I want to stakeholder is 4. This is due to Barago and Ivanov. And they looked at the collection of n-dimensional Finsler manifolds. Maybe put a star here, because then there's some more assumptions. I wrote them down here. C2 metric, and you want strictly convex norms. So I'll write it with C2 metric and strictly convex norms. I'm not worried at all about this. And these things admit smooth isometric embeddings into finite dimensional Banach spaces. All right. And so, say a few words here. Finsler manifold. There's a more abstract definition than what I'm about to say, but the way the class of manifolds I like to think of that live here, proper subclass, is take your manifold, and you're gonna, for a Riemannian manifold, you have a smooth assignment of a positive definite symmetric bilinear form. Here, you want to take a smooth assignment of a norm on the tangent space at each point. Finsler, the definition's a little more general, but that's a nice class. Of course, not all, right? Some norms give you an inner product, but not all, right? So in general, what I just said is already a bigger class than Riemannian manifolds. So you have norms that don't give you an inner product, right? So maybe the upshot is it's unlikely that you're going to be able to put Euclidean space here because you have norms that don't come from dot products, right? But they look at just finite dimensional Banach space. They put norms on Rn. And they actually, from my understanding, they cook up the norm from the Finsler norm you're given here, right? So given a Finsler norm with these assumptions, they then use that to cook up the norm that you're going to put on Rn as they go through, which is neat. And so, the thing I just alluded to, that's actually a theorem. This is a negative result.
Does finite come with a bound in terms of the end?
Oh, yeah, it's a good question. Generally, no. For a given metric, you then get a bound. But if you fix your manifold and let different norms, you get different bounds. And I think they prove you can go up to infinity. You can't. I'm trying to remember through their paper, their construction. I think they show that has to happen, but it might just be that their proof, it cooks up that way. I can't remember if it's a necessary deal or not. But yeah, the dimension totally depends on the norm they get. Excellent. Yeah, it's good. Yeah, all right, so negative result is written down by Ledone. But this was definitely known by Anton Petrun. And he says this in a paper, but doesn't really elaborate, and then Ledone writes it down a little bit later. Barago probably knew this too. And by the way, it's probably not too nice to call someone else's theorem a negative result. Not negative. Hey, the result is that any Finsler manifold, which is not Riemannian, does not admit a path isometric embedding into Euclidean space, En for any n. So in particular, if the norm here doesn't give you an inner product, then you can't. It doesn't admit a path isometric embedding into Euclidean space.
So, can I ask?
Yeah, absolutely.
What did you make some additional assumptions about the geometry of the manifold? Something about curvature? Does it change the bounds of the dimension? Is it make it better or worse?
I don't. There's not a lot. I was surprised about that. Me and Lafont were talking about that one time. There's not a lot known about how curvature bounds play into the dimension. They should at some point, right? Negative curvature tends to force higher, right? Like,
Exactly, right.
It tends to be higher dimensions, but that's just. I don't know if there's specifically a rigorous statement proved. It's just that that's kind of. There are people that study. So I should say this. I'm about to say this in a second. The C1 Nash and Nicholas Kuiper, his version of the C1 isometric embedding theorem of Nash proves that the hyperbolic plane admits a C1 isometric embedding into E3. C1, not smooth. Matter of fact, not C2. Curvature reasons, you're not, right? For curvature reasons, it's not C2. C1, it's a kind of a pathological map. So then you can do kind of that Holder continuous stuff. You can ask, what values of alpha can you get C1 alpha, right? What values of alpha? And I think there are a lot of people that study stuff about this. I'm not one of those people. But I've seen different papers so there's something where the curvature, but not, yeah, that's not my area. But. All right, so the last thing I want to say here is I erased the Nash stuff. Probably not the best idea. So the Nash stuff was you had I can write this real quick, Riemannian manifolds. And you had C1, you had smooth, E2n plus 1, and big N for that big N. Some of these results, this one here, to this one for sure. And this one, but you need to get rid of smooth and instead put C1. Yeah, those three, those results have approximate analogs. Star, in this case, means have approximate analogs. And what do I mean by that? Right? Explain what that means. So what Nash proves here isn't just that there exists a C1 isometric embedding here, but that there exists lots of them. Lots and lots and lots of them. What he proves is that if you have any embedding that's one Lipschitz and you have codimension at least 2, then you can perturb it to be a C1 isometric embedding. You can approximate. I'm going to draw a picture in a second. And then Nicholas Kuiper lowered the codimension to 1, and that's where the H2 and the E3 played a role. So what's the picture? Is if you take, put it here. Right, if you've got some manifold, right, and you've got some path, right, I don't know, let's just say the length of this path, let's say it's 100, I don't know. Right? And you map this into Euclidean space. Right? I'm not going to try to draw the whole, but you just look at the path, right? That path. And let's say that the length of f of alpha, I don't know, let's say it's 1. Right? Then if I just look at a path, it makes sense that I can find a nearby path, right, where the length is 100. I take the path I originally had and I do this. Right? And you can find an arbitrarily close path whose length will be the length you had here, right? And so in particular, if your map is 1 Lipschitz, meaning that if you take distances are shorter than or equal to what you had over here, right? Then you have hope at least of just kind of wiggling the points and getting a map that preserves the lengths of paths, right? And again, in this case, Nash does a C1 results in that case, the C0, and you can do a C1 version of that here. Here it's actually cooler because, not cooler, equal, cool. But because you have positive and negative directions, you don't need to be one Lipschitz anymore. The set of C1 isometric embeddings of n-dimensional manifolds with indefinite metric tensors into RQQ is dense within the collection of all continuous maps. Any continuous map you can approximate by smooth map and then use both the positive and negative to move stuff around, which is pretty cool. But quotes aren't cool, right? We're in a math seminar, right? So cool, right? That's all right. What Nash actually does in his C1 paper, which is cool, say a few words, is he doesn't do this wiggling. I said he need codimension 2. That would only be 1 if you could pull that off. What he does is he spirals. Maybe you get rid of it. Nash spirals the entire embedding. Not just of this path, but you take the whole map in, and then he does a spiraling technique on the whole embedding, which if you're one Lipschitz, distances are shorter over here, and he spirals to fix close to half of the error, right? Whatever the metric is minus the induced metric, right? And then he does that again and again and again, and then in the limit, it gets a C1 map. Which is, yeah. And Kuiper did the wiggling part after. So. All right, so manifolds, it's part 3. I'm going to talk about what I'll call polyhedra. So this is attempts now to generalize these results but to a different class of spaces. And so maybe first, all I mean by polyhedra, I just mean a simplicial complex. Maybe I should just write the word simplicial complex. Polyhedra, I just mean some pair xt where X is a topological space, and T is a simplicial triangulation. And of course, then I want to put piecewise flat metrics on such things, right? That's where we're going here. And so, two classes of piecewise flat metrics that I want to look at here. The first I'm going to call Euclidean polyhedra. And the second, people like to said my Riemannian yesterday, but I'll stick with what I call the paper. Called indefinite metric polyhedra. Right. I've got big wordy definitions here in my notes, but I think what I'll do is I'll just get the point across and draw examples, right? I think you get the examples and then you can write down. Definitions are easy, right? This is supposed to be an analog to kind of PL Riemannian manifolds, but of course they don't have to be manifolds, right? Just simplicial complex. And then this is going to be the analog to those indefinite metric tensors on manifolds, right? It's just a kind of PL analog. And so what do you have in both cases here? You want a piecewise flat, or assign a flat metric, or quadratic form, right? Or quadratic form to each simplex. Right? You're going to do the same thing here, right? We're metric, right? Quadratic form. And then you want glue together by isometries. Glue simplices together by isometries. All right, same setup, so isometries. But then in the case here, you want your forms to always be positive definite, and here you don't care what the signature of the form is, right? It's the difference. So here, quadratic forms are positive definite. And here, quadratic forms can have any signature. If you want all k simplices here admit linear isometric embeddings into EK, right, for any K. Here, all K-dimensional simplices admit linear isometric embeddings into some RPQ, where P plus Q is K, right? Now you can word that.
But you always want something compact or not necessarily?
It doesn't have to be compact. Locally finite, that's important.
But you identify
Thanks.
some spaces, but not.
It could be infinite simplicial complexes, and it's going to be simplicial. No, you look at no delta complexes like in Hatcher's book or any of that type of stuff. The simplicial, but do need locally finite. Nothing. Yeah. Thanks. That's good. Some results would be better for compact. I'll get to that. So here's maybe some pictures, examples. So copying from my notes, but it doesn't matter. Oh, quick remark, I just saw it in my notes, I'm glad. Obviously, positive definite is any signature, so these are proper, not equal, proper subset of those things, right? It's worth pointing out. All right, examples. Let's look at this Euclidean. And these are the indefinite metric. Right, and so just kind of stupid example. Draw the 2 simplex, put an edge on here, give lengths, I don't know, 4, 4, 6, 200. Right, it's perfectly good Euclidean polyhedra, right? Nice. Not a manifold, but yeah. Nice. Here, indefinite metric, let's do the same thing. But as long as you're careful with what you're talking about, you can have different signatures, so you can put negative, right? So I'm going to do like something -5, 17, -21, again, 200, right? When I say negative here, maybe I should be a little careful. What you mean is that if I take this vector here, v, if I take whatever the form is, v dot v with whatever form I have, this gives me -21 squared, right? Right, does that make sense? Right, is that good there? You could talk in terms of energy and square things, but if you do energy, it's not as obvious when things satisfy the triangle inequalities. It's better to keep lengths and, right, and play around with that, right? It's worth pointing out, if I take this -5, -21, 17, you can check that this triangle lives in R11, right? It has signature 1, 1. You can, it's not, I swear it's not that bad. Right? And so let's do maybe another example. Let's take a one-dimensional simplicial complex. It's boundary of a triangle, but hollow, so one-dimensional. Let's stick edge lengths. 1, 1, 100. That's a perfectly fine Euclidean simplex because there's no interior. It's hollow. It's a metric space if the distance between points equals the infimum of the lengths of paths. So the distance as a metric space from this point to this point is 2, right? Because I have a path that goes there, and there's no shorter path, right? This means that the length of that path is 100. Doesn't mean the distance is 100, right? So it's a perfectly fine metric space, right? You put infinite paths there, right? It's perfectly fine construction, fits into the definition. Of course, if I want to come up with an analog over here, let's put the 1, 1, 100, but now fill it in. Now that's not positive definite anymore, right? And you can check again. This lives in R11. That's signature 1, 1, right? It's not too bad. Yeah. Is this all right? I'm good. All right. So
But this is still allowed, right?
yeah, it's allowed in here. In here, yeah. That's allowed here, right? Yeah. And so now, when you talk about manifolds, what kind of maps did we talk about? We talked about smooth maps, C1 maps, and there were C0, the Gromov stuff, the continuous. So what types of maps do we want to look at? Types of maps. All right. 3 classes we're going to look at here. We're going to look at simplicial, piecewise linear, and continuous. And this will have the analog, kind of the smooth class, right? This will kind of have the C1 analog, and that is C0, right? That's fine, right? And so let me say words. When I say simplicial, I mean linear on the given triangulation. So you've got your space and you have some God-given triangulation, right, handed to you. Linear on the triangulation you're given. This means linear on some subdivision of the given triangulation, right? Is that right? And then continuous, right? No. Oh, I just erased this. Sorry. If you ever, so I was calling these things Euclidean polyhedras, remark real quick. If you look, in some places they call these polyhedral spaces. I'm saying Euclidean to stress that these are flat simplices. Polyhedral spaces, they sometimes use spherical simplices or hyperbolic simplices. The results I'm about to say have some analogs there. I wasn't not too worried about it. But the point in Euclidean was to stress the flat Euclidean simplices on everything. All right, so yeah, known results. First, maybe big known result is this was it's due to Sletvina Krat when n equals 2. And then it's due to Arsenia Kopion. And this is for all n. Right? And the result is it's an analog of Gromov's elephant map. And if you look at the class of n-dimensional Euclidean polyhedra, these admit PL isometric embeddings. So maybe if you think of PL as being like C1, it's even better. It's more like the Nash elephant map, but Nash's stuff. PL isometric embeddings into E, same dimension. Right, so just like the elephant map that's stepping on. Right? Not embeddings. Oh, crap. PL isometry. Not embedding. That's the whole point. Right? So when I started working on this stuff, I was specifically looking for isometric embeddings. So saw this real nice. This was all in Russian. A copy on, not Russian, but one of the former Soviet Union countries. Armenian, right? And so yeah, I couldn't read any of this. So, Anton Petrunin was very nice. Sent me an email with the contents in the paper. It was pretty awesome to him. Wanted to try to emphasize that. So yeah, so I was concerned about embeddings, and so you look at the class of n-dimensional Euclidean polyhedra, and what I was able to prove is that these admit PL isometric embeddings. For free from that, and I'll explain this in a second, you get E3n plus 1 kind of for free. And this is a trick, I was able to take one dimension off. I wish I could do better than that, right? But I could remove one right after. But yeah, I can get continuous isometric embeddings all the way down to E2n plus 1, which you'd hope for. I can get continuous, but it's a limit of subdivisions, so in the limit, right, it might only be right continuous. But yeah, how you get the 3n plus 1 for free is you take an embedding into 2n plus 1 that's one Lipschitz, and then apply their theorem in the other n dimensions, right? And then concatenate them, right? And you get 3n plus 1. All right, so now, but where I started all this stuff was with the indefinite metric stuff. So this is the nicer stuff here. You look at the class of n-dimensional indefinite metric polyhedra. And these admit simplicial isometric embeddings into some RQQ. I'll say what Q is in a second. I'll erase the board and write it down. And then they admit PL isometric embeddings. Maybe put R, the Q, so let me do P. The P here is lower. It's just you use the crowd a copy on result and apply it here. And so in this case, you get p greater than or equal to n, and 2p, you need at least 3n dimensions, right? Right, 3n because I had the same problem as I hit there, right?
You know, 3 years.
Yeah, so what I did here, I messed up, it looked like here's the actual result. PQ, P greater than or equal to N, Q greater than or equal to N, P plus Q greater than or equal to 3N, right? You can hook up different negative for different, and then I stated something real dumb there. Thank you, I did catch that right as you were saying it. I was like, wait a minute. That's what I get for trying to cheat from the minutes mid-talk. So what is the Q here? The Q here is the maximum of 2n plus 1 for embedding, but then it's also the maximal degree of any vertex in your triangulation. Degree or valence, right, if you like the word valence, right, of any vertex in your triangulation. Of course, if your space is compact, that exists. If your space is not compact, then you need to assume that this exists. The maximal degree of any vertex is bounded above. You make that an assumption. I cook up examples that show that in the compact case, this is necessary. You can't get rid of that. That's right. That's required. This is as good of a requirement as you can do. Also, yeah, in the non-compact case, I give examples where you need this assumption, right? If you don't have this assumption, then there aren't some partial isometric embeddings. 2 students working with Sergey Ivanov. So I got the non-compact case here. Let me put a star here and I'll explain a different star. Now explain the star. 2, I got the non-compact case, but I got really high dimensions, much bigger than this. But I showed that you needed this bound. And then 2 students working with Sergey Ivanov showed that in the non-compact case, you can get this exact same dimension. So this is this in both cases. It's in the students are Galashin and Zolotov. Sergey got the same dimensions for non-compact.
And 3 years can't be improved?
Oh, probably can. If you could improve this, then you can improve that. My guess is that you can probably, that would be my guess. I don't know how to do it. And if you could do that, then you could do that here. You can also hook up, I ran out of room on the bottom of the board there. You can take this crowded copying result, if you don't care about embeddings, just PL isometries, and you can do that same thing here, and you just need P and Q both greater than or equal to N. You can get rid of embedding, right? Do that as well. To answer your question is, I think it can. that would be my guess. Right? And then a lot of these have approximate analogs, the same type of 1 Lipschitz. You can this set of maps here are dense within the collection of all 1 Lipschitz maps. So then the same here, not there, but here, and then for the other analog. These would be dense within the collection of all continuous maps, and then here for 1 Lipschitz maps, right? All right, so that's good. So the last part of the talk, title of the talk was the isometric embedding problem for length metric spaces. So that's for the last 7 minutes. Let's talk about length metric spaces. All right, and so say this all right. A length metric space is a metric space where the distance between any 2 points equals the inf of the length of paths between those points. It's a geodesic metric space if you have it, if that inf is realized, if there exists a path between 2 points that realizes the distance, length realizes the distance. So this is like these length metric spaces. They're kind of, if you're looking at path isometries, maps that preserve the lengths of paths, this is the kind of the largest ambient set you want to look at, right? And so, by the way, this was the problem my advisor gave me for the PhD problem way back now, lots of years ago. When we look at n-dimensional covering dimension, length metric spaces, length metric spaces. And the question was, do there exist path isometric embeddings into Euclidean space? This was the question, right? Something to work on. So started working on this. I went to the simpler case of the Euclidean polyhedra, found that, and did this indefinite metric stuff. Thankfully, was able to graduate. But yeah, tried working on this. Of course, if you guys remember the negative result, this is false. It's not true, right? I don't know where to put the x. Seems like a good place to put the x. This is false because Finsler manifolds sit in here. They're length metric spaces, perfectly nice length. They're really, really nice length metric spaces, and they don't admit path isometries to Euclidean space, right? I mean, examples of length metric spaces: Riemannian manifolds, Finsler manifolds. If you know what sub-Riemannian or sub-Finsler structures on manifolds are, right? Those work. Those Euclidean polyhedra, Alexandrov spaces, cat K spaces, right? And those are the really nice ones, right? They have nice curvature bounds. In general, these things are, it's a giant class of spaces. So it's probably unrealistic to hope for that. But as a grad student, I didn't know it wasn't true yet, and so I worked on this real hard. I got really close to proving it. Thankfully, I never said I could prove it. It was false, thankfully. But I tried. I got real close. So after I graduated, I was thinking, you know what? Can I use any of that, and can I say anything? And so the answer is yes, I can say something. But I need to make two changes. First is I need to change this. I need to put R, big N, comma 1. I need one negative direction. And then I need to switch path isometry to what I call an approximate isometry. I'll explain. Still an embedding. Embedding's good. That's fine. But the isometry part. So let me write down an actual statement. So call this main theorem, whatever. Yeah. Theorem. I should write a statement here. Let Xn be a proper n-dimensional length metric space.
Dimensional meaning what?
Covering dimension. That's it. Excellent. Any open cover has a refinement that has order n plus 1. Topological dimension. Yeah. Length metric space, and let D, script D, subset of X, be any countable dense subset. Then there exists a collection of geodesics capital gamma associated to D and an embedding F, which goes from your space into R. I needed 3n plus 6, comma 1, right? Positive 3n plus 6 positive, 1 negative, and embedding blah, such that the energy of some little gamma equals the energy of F composed with gamma for all gamma and big gamma.
Associated with D.
I'm about to, yeah, excellent, good. All right, so maybe go through here real quick. That's the main question, right? Proper just means closed bounded sets are compact. N-dimensional is topological dimension or covering dimension. Countable dense, good. What do I mean by collection of geodesics associated to D? Quantifiers are important here. What it means is that for any 2 points in D, there exists a geodesic in gamma connecting those 2 points. Not all geodesics. You construct the geodesics as you go, right? Given the countable dense subset, you cook up the geodesics as you go. Let me, as I see people trying to write this, I'm going to take the same this sentence here and rewrite it right up here so people can read it.
And the conclusion was, so the lengths are the same? So what?
Energies are the same. Energies are the same. So geodesic gamma associated to D and an embedding F from X, R, and 3 such that the energy of gamma equals the energy of F composed with gamma for all little gamma and capital gamma.
So how is it different energy? Is it different from lengths?
All right, so why do I use energy and not length? This is a question. Make this a joke. So the reason I mean, sometimes there's deep reasons, not deep. The reason I use energy is because that's a square root, and that's a negative sign. And so you've got to deal with potentially square roots of negative numbers, right? It's Lorentzian space. You have Lorentzian space. I need one negative dimension, right? Yeah, and so I need energy, just get rid of the square root. That's all. Sorry, yeah. My handwriting's never good, but on the bottom of boards it's way worse because I'm pretty tall. So 1 minute. First, so 1 minute, real quick. This one negative dimension is necessary here because if you remove it, that's a metric space, E 3n plus 6, and then a dense set, you get path isometry everywhere, and it violates the, right? So you need this one negative dimension. But it's only some geodesics connecting a countable dense subset. And an addendum to this is that you can construct this map F so that it's not locally Lipschitz. And my guess is that it's always not locally Lipschitz, meaning that essentially, don't rigorously prove this, but this is true. Any path not in gamma is going to have infinite energy under this map F. You blow up the energy of all other paths. You preserve the energy of the paths in this nice chosen set, right? And then all the other ones, they get giant energy. You blow the metric up as you're going, right? So it's kind of like a pathological deal. It's a whole limiting process.
I don't know. I think not always. There are probably situations that not always.
Sure. When if you get nice space, right? Well, so yeah, it's worth pointing. I mean the map F that I construct, not that there doesn't exist an F where you, yeah, they're almost certainly in nice examples would exist a nice F, right? The F that you construct from, so this theorem is semi-constructive. It's a limiting process, and the F that comes out of that, I think, would always have, because you're blowing up the metric as you go. Say real quick, because I'm about out of time. I was just going to give a 1 minute sketch, not how to prove it, but the idea. What you do is you write countable, how you use it, is you write this as an increasing union of finite. As you're going, you cook up these geodesics among the finite points, and then as you add an extra point, you make new geodesics and keep going. You use those finite collection of geodesics to cook up an open cover of your space, right? And as you add more and more geodesics, you keep the covers finer and finer. You get a refinement. And then from each of those covers, you associate the nerve, right? And so you've got your space, and you've got a bunch, and then you put Euclidean metrics on those. And so you've got these polyhedra. They end up being like n plus 2 dimensional, where that's n dimensional. K, P, K minus 1, and you've got maps, right, this way, maps down that way. X ends up being the inverse limit, topologically, of the nerves, but it's not the inverse limit from a metric standpoint. The metrics here do not converge the metric there, right? But so then you map all these into R 3n plus 6, 1, right? And it ends up being the limit of that, the composition ends up being what works. And it's not real restrictive on the geodesics. I go 30 more seconds over. The only thing, when you pick these geodesics, all you don't want, if I have this geodesic here, I don't want my geodesic from here to go like this. All you do is, if that's your geodesic, you just replace it by this geodesic. So you intersect in either a point, a line segment, or you don't intersect at all, right? It's just make them behave nicely. That's all. Sorry, 3 minutes over, my bad.